Hello, my name is Dr. Owena Christensen, and I would like to thank you for your invitation to speak to you today. It's my pleasure to share with you some of my thoughts and insights relating to human reproduction in space, some of the challenges and some of the conundrums, and in the second half of the presentation to have a bit of a special look at children's health in space. You might say that this topic is somewhat of an elephant in the room. However, it's something that humanity is going to have to address and bring out into the open if we want to become a true spacefaring species, if we want to form settlements on the moon and on Mars and perhaps other places in the distant future. And I'm sure you've probably all learned about the principles of evolution and natural selection when you were at high school. And we really have to think about the possibility that if we have pregnancy and childbirth in space, that we might end up evolving a new race of humans. So there are some really interesting ethical questions to think about as well. Today we're going to cover a wide range of topics. We've already had a teaser about pregnancy and childbirth in space, and if we might end up evolving a new race of humans. We're going to touch briefly on the space effects on human reproduction, the need for appropriate medical care, the impact of gravity, which is a really critical issue in all of these questions, and then looking at the rights of the child in space and extreme environments, early development and radiation effects, child growth and development, challenges for child health, looking at conception in space, the idea of using space tourism for this purpose, and then concluding remarks and answers to questions. All human space missions have limited crew capacity, and so one question we need to think about is, do we take a doctor? What type of doctor do we take? And of course, things like emergency medicine, possibly surgery, they're the most obvious things that leap out at us in terms of medical care. There's also going to need to be general practice or family doctor type care as well. But if we're turning to consider obstetrics and pediatrics, they really require specialised knowledge. And so we will really have to think hard about, do we take generalists or do we have to take specialists, or can we take both? But when we have very limited crew manifests, it's always going to be a bit of a balancing act. And that also brings in the ethical considerations around, do we allow pregnancy and childbirth in space? Do we bring up children in space? And so on. We also need to think about communications and evacuations. If we're in low Earth orbit or on the moon, the communications delay is not very significant. But if you're out at Mars or on the way to Mars, it could be up to 24 minutes each way, depending on distance. Evacuation is definitely possible from the ISS. It's probably also possible from the moon, depending how urgent the situation is, but it's completely unrealistic for Mars. So then we need to be able to turn to a couple of solutions. If we can't evacuate quickly, telemedicine is very useful for advice and instructions, but it is dependent on the availability of electricity and suitable technology, and also good space weather. So this should only be used as an adjunct to a largely autonomous expeditionary health service, whether this is on the ISS, in space flight, or with colonisation. And the further out you get, the more problematic timely access becomes. And in the absence of telemedicine, astronauts will need to rely on their own knowledge base, training, skills, good teamwork, and access to a large digital database of medical information. The rules are pretty simple at the moment. As far as pregnancy goes, pregnant astronauts are not allowed to fly, full stop. And if we look at children under the age of 18 are currently not allowed to fly on space flights in the USA, at least. And there was a question about citizenship. And according to Article 8 of the Outer Space Treaty, children born in outer space or in constructed objects, for instance buildings, within a space settlement, will not be stateless, but they will have the citizenship of the nation that controls the object. So if it's a European habitat, for instance, the child will have European citizenship. I am not going to go over too much on this slide because I know that Dr. Jane is also speaking to you today, but I just did want to highlight the space radiation effects and the damage that that can cause to DNA and that it can cause to germ cells, such as the ovarian egg producing cells and sperm in men, and the implications that that then carries for genetic mutations in offspring and also sterility or infertility. Now let's move on to gravity, which is perhaps the biggest elephant in the room. So gravity, it's something that we've all grown up with. It's something that we don't really think about on a day-to-day basis. It's often quite useful. Sometimes it's annoying, for instance, when things fall onto the floor. But it's really important to think that every single piece of life that has ever evolved on Earth has evolved to withstand the force of gravity in order to retain its structure, apart from one weird fish which is flat because it can't withstand gravity. So how long has life been around on Earth? Well, probably about 3.7 billion years. And the stromatolites that you might have heard about, they date back to 3.5 billion years ago. So that's a really, really, really long time that life on Earth has evolved with gravity. So how long have humans been around for? Probably 550,000 years ago. That was the beginning of the Homo sapiens lineage. About 50,000 years ago, people were moving out of Africa. And then between 15,000 to 40,000 years ago, Homo sapiens became the only surviving human species. And if you contrast that with the amount of time that we've been in space, it's only 60 years ago that we had the first manned space flights in April and May 1961. And we also need to think about different gravitational environments and transitioning between different gravitational environments. So we have 1g on Earth, 1/6 of the Earth's gravity on the Moon, 1/3 on the Mars, and the larger the planet, the larger the gravity. There are just two things I want to point out on this slide. The first is that in order to conceive, to be born, to be reared, there are many intricate and complex phases of reproduction which all need to go right. And you also need your hormonal systems working properly. And there's been evidence of hypothalamic neurochemical disruption, especially with oxytocin, which we all know as the bonding hormone. So that could have implications for child rearing. There's officially never been sex in space, but it's an interesting prospect if you think about the principle of for every action there's an equal and opposite reaction. So you're going to have to be able to keep people together for long enough. And we also need to bring into our thought experiment the question of what the lack of gravity will do in terms of normal reproductive processes. So will sperm know which direction to travel in? For instance, they're probably quite accustomed to traveling against the force of gravity and perpendicular to the force of gravity. So if there's no gravity, will they be able to orient themselves correctly? If we then turn to thinking about the egg, will it know what direction to travel in? Will it need to know that it has to go up the fallopian tube a short distance, then it has to travel down the fallopian tube, which would normally be perpendicular to the force of gravity, and then it has to go down into the uterus to implant, which would normally be in the direction of gravity. And if the egg doesn't know where to go when it's in the fallopian tube, will there be a higher risk of ectopic pregnancies? And then there's another really interesting question of what happens with the normal physiological changes in pregnancy that fertilization and implantation will prompt. Relatively speaking, very few women have flown in space, and at the moment we don't have a really comprehensive understanding of normal female physiology in space. And if you think about the vast array of physiological changes which normally occur in pregnancy, we really don't know at this point if they are going to be adaptive or maladaptive in space flight. So that's something that's going to need to be explored quite closely before we know if it's safe to send pregnant women into space. There are also challenges if we think about the immunocompromise which occurs in space, with the greater risk of contracting illnesses and the extra stress that pregnancy brings, if that might have a further cumulative effect on the immune system. Now there's a lot on this slide, but in essence in rodent studies fertilization was possible, but embryonic development was often delayed or arrested. Some pregnancies were reabsorbed. Also evidence of early pregnancy lost, and the limited data indicates that spaceflight and microgravity adversely affect very early embryonic development. But development during the second half of gestation proceeds fairly normally. So that's a little bit like what happens with humans, that the greatest risk of teratogenesis and malformations occurs early in the pregnancy, and things are more stable in the latter half of the pregnancy. Also interesting research to show that rats needed more contractions to deliver their young because of the alterations in abdominal musculature due to gravity and the decreased uterine expression of connexin. So this is a table from one of the research studies relating to rodents and highlights the prevalence of outcomes such as spontaneous abortion, reduced gestational weight, reduced birth weight, and reduced survival for offspring. And these negative effects didn't only occur in microgravity, they also occurred in hypergravity. And you might say, well, why does hypergravity matter? And that is because of the transition between gravitational fields. So if we're talking about Earth and Moon and Mars, then we have 1G, 1/6G, 1/3 G, microgravity. And if you're moving from a low gravity environment to a higher gravity environment, then you're moving from a essentially hypo to hypergravity environment. So that's where the implications of that could come in. This is a summary of various research studies. So it was also looking at the possibility of pregnancy. Births are possible but likely to be more difficult, likely to be more stillbirths. Environmental factors such as low gravity and cosmic radiation and solar flares can all have quite negative effects on fetal development. That microgravity can also disrupt the development of the vestibular system. So this could have implications for a child who's conceived in microgravity, then coming into a gravitational environment. Also effects on human bone marrow stem cells and reduced cell proliferation. This could result in developmental abnormalities. And then we start getting into the ethical arena, because if you have a child with birth defects or one born prematurely, that child's going to be more difficult to care for in an environment which has very limited resources. And another concern is contamination of the filtered air and presence of high levels of carbon dioxide, both of which could be harmful to a developing fetus. And if we think about the actual process of birth, normally babies rotate head first prior to delivery, but in the absence of gravity, will the baby know that it needs to rotate head first? And if it doesn't, will there be an increased risk of breech presentations where it presents bottom first or bottom plus one or other limbs? And as a result, will there be an increased incidence of positional birth complications and a need for interventional deliveries? Giving birth is a very dynamic process with lots of pushing, so we need to think about the laws of physics as well. It's also messy, lots of fluid and blood, and fluids behave differently in space. Venous blood adheres to surfaces due to surface tension, but arterial blood tends to spurt out and form droplets, which can cause contamination or block the field of view. And we've mentioned about the increased number of contractions needed due to weakened abdominal muscles. Any kind of emergency cesarean surgery is going to be challenging because surgery in space is challenging. And the use of inhaled anesthetics such as nitrous oxide, which is commonly used in obstetrics, is problematic if you have a closed environment because you can't filter them out of the air and they may affect other people. Now I'm just going to say a few words about the practicalities of caring for pregnant women in space. And it's useful to note that in 2011, the United States Antarctic Program instituted a new rule requiring all women of childbearing years to take pregnancy tests before being cleared to live in Antarctica, and female astronauts also need to prove that they're not pregnant. But if we're thinking about long duration space travel, things can happen, but can we really provide the necessary pregnancy-related care? We're not going to be able to evacuate people, we're not going to be able to receive resupplies, and there's also the issue, which perhaps you wouldn't think of immediately, but apart from the risk to the pregnant mother, there's also the other members of the crew and whether they're going to be equipped to deal with any emergencies. And if they don't have the skills or supplies necessary to keep a mother and child safe and alive, for instance, this could cause enormous psychological trauma for the whole crew. If we turn to looking at the rights of the child, there's a United Nations Convention on the Rights of the Child, which has 54 components to it. And we really need to think very carefully if we can supply any or all or most or few of these rights the children are entitled to on Earth. And if we really can't do that in the space environment, then should we be having children in space? In medical school, we're often encouraged to take a biopsychosocial view of the person and have a 360-degree view with situational awareness of the context that they're coming from. The average person, when you talk about health, they probably would think immediately of physical health. Maybe people are becoming more aware of psychological well-being as well. But the determinants of health generally are much broader, and some of the things in those determinants of health have per se nothing to do with health. And for instance, food, education, work environment, water and sanitation, your built environment, the environment that you live in, the air that you breathe, any pollutants that are present, access to public and green space, really important for psychological well-being, as is non-discrimination, equality, peace and inclusivity. Earlier on, I mentioned the issue of whether we can actually accommodate all the rights of the child in space, and equally, can we accommodate all the social determinants of health that are going to result in good health and well-being? And one really important factor when we're thinking about going from Earth to Mars particularly, is radiation. And on the way, going to encounter quite a lot of cosmic radiation, relatively speaking, maybe some solar flares. And on the surface of Mars, there's going to be a lot more radiation than there is on Earth, because Mars has a much thinner atmosphere than the Earth. So why is radiation important? Well, ionizing radiation in particular is a known carcinogen to which children are particularly vulnerable, and the sensitivity to radiation is highest early in life. And this is likely to be linked to greater cell division in growing and developing tissues. And also because children have a longer expected lifetime, there's going to be an increased chance of repeated exposure and accumulated damage. And all of this collectively leads to a higher cancer risk for children. And it's important to note that fetuses might be particularly sensitive to ionizing radiation, since their tissue cells are undergoing high rates of division and are also differentiating into mature functional cells. I'm now going to return to the topic of gravity and why it's important if we're thinking about fetal growth and development. And that's because gravity determines the shape of body tissue and affects all the functions of life, both in plants and in animals. It regulates cell proliferation, plays crucial roles in cellular function. For instance, we regulate the densities of our bones and muscles in response to gravitational load. And this beautiful paper has actually identified the protein which appears to be responsible for the ability of cells to withstand gravity and allow them to generate a three-dimensional body or organ shape. And the authors are also hypothesizing that this protein is involved in the maintenance of bones and skeletal muscles, as well as controlling organ size. So if we're thinking about space, we need to think about this protein, which affects the cell fate of bones, muscles, and stem cells. If we're talking about child growth and development, brain growth keeps accelerating through infancy, early childhood, middle childhood, and then tapers off in adolescence. Body growth goes through a few spurts until it tapers off in adolescence. So these are both continuous processes through infancy and childhood. And bones are going to want to be able to grow, to become strong, to ossify, and skeletal muscles also need to go through that same process. However, if you look at this picture on the bottom, and this is hypothesizing what will happen to bone strength, muscle strength, as you go on the outward flight to Mars and then the return flight. So potentially there's going to be a continuous downward trajectory. And you really have to think about how these two trajectories would interact. The upward trajectory needed for normal child growth and development, and then the downward trajectory, which, unless compensated by countermeasures, will occur as a result of microgravity affecting both bones and muscles. And I'm going to talk a little bit more about how children actually learn to be human beings as they go through infancy and early childhood in the next slide. But one issue that I want to mention is that fractures in childhood are relatively common because children like to play, they like to do adventurous things. And if you have weakened bones and skeletal muscles as a result of insufficient growth and development due to microgravity, then they're going to be at more risk of fractures, particularly so if they come into a gravitational environment with weakened bones and muscles. Now, I'm not going to go over this slide in detail, but the point of it is to demonstrate just how many processes of children becoming little human beings are dependent on gravity. Things like the baby needs to learn to raise its head against gravity. It needs to learn to roll over. It needs to learn to sit up, to crawl, to stand, to run. And all those actions involve acting against gravity to some degree or another. So there would be a real challenge for children to actually learn these actions and to go through these developmental milestones if there is no gravity to work against. On Earth, we have a number of mechanisms working together that we can thank our balance and proprioception for. We have our eyes, we have the vestibular system in the inner ear, we have the receptors in our muscles and joints, and all of those work together to help us to know where we are in space and what direction we're moving in. But in space, there's no up or down, and so there's conflict between what the eyes see and the perception of motion and orientation, which then happens in the brain. And there was that really interesting study I mentioned earlier to demonstrate that unborn rat fetuses returning to Earth demonstrated an extreme sensitivity to positional disturbance, and that probably reflected that the vestibular system had not developed in the same way in space as it had on Earth, and their nervous system was just not used to the constant pull of gravity. As well as bone and muscle development in microgravity, it's important to think about early brain development and health. Important to remember that the brain starts growing before birth and then continues into childhood, and that the first 8 years are perhaps the most important for building a future foundation. And how well a brain develops depends on many factors in addition to that person's genetic makeup, including proper nutrition for the mother in pregnancy, exposure to toxins or infections, and the child's experiences interacting with other people and the world. And being able to provide nurturing and responsive care for both the child's body and mind is really important in supporting healthy brain development. And remembering that it's a combination of positive and negative experiences that shape a child's development. So we need to be able to provide children with the right care starting before birth and continuing through childhood. And we really have to think hard about whether we can provide that adequately in space. And it's not just thinking about physical development, it's also thinking about how children learn, how they develop language skills, how they learn to play, all the things that we take for granted on Earth when we're bringing up children, and kids have access to heaps of toys, playmates, stimulation. And all of that is also really important for neurological development. So we need to ask once again, can we provide that sort of rich, safe environment in space? The mother's health and nutrition during pregnancy is incredibly important. Folic acid, for instance, for neural tube closure. Vaccinations are important to protect pregnant women from infections. So are we going to be able to provide those in space? What's the risk of being exposed to infectious diseases in space? What's the risk of being exposed to toxins? Here on Earth, we normally have newborn screening, which can detect a whole lot of dangerous conditions. Will we be able to provide that in space? And children are particularly vulnerable to traumatic head injuries, infections, and toxins. So we need to think about protecting them from risk in space. We need to think about, can we give them childhood vaccines? And making sure that they have access to healthy foods and places to live and play. So once again, can we actually do all of that in space? In terms of neurological development, there's concerning evidence from existing knowledge about neurological effects of long-duration spaceflight on adults, and therefore it would be a reasonable hypothesis that children would not be immune from these effects, and the resulting impact on the developing brain is an unknown. So spaceflight stressors to the brain include microgravity itself, radiation, isolation, confinement, circadian disruption, impaired sleep quality, and hypercapnia. So children could experience all of those things as well. So why is this slide here? Basically to show that there are still a lot of challenges to child health and surviving to adulthood here on Earth, whether it's infectious disease, chronic disease, cancer, trauma, and all the other causes of childhood morbidity and mortality. And children aren't going to be immune from those in space. We can't possibly make them totally immune. So we have to face the fact that there are still going to be challenges to children surviving. Even if there's no infectious disease within the spacecraft or within the colony, if you go back to an environment where there might be disease, then if you're not vaccinated against common childhood diseases, such as this vast array of vaccinations that we provide for children, then you could be in trouble. People tend to forget that some of these diseases are very serious and used to kill lots of children. And I think that's an issue that we need to take seriously if we are going to think about having children in space. It's not only children, we also carry vaccinations forward into adolescence and adulthood. And you might say, well, there's no infectious disease on our spacecraft or on our colony, but there's always going to be the possibility of introduced disease that might slip through the cracks. And we've certainly seen that with the COVID-19 pandemic. Now, to finish on a light note, some people are actually suggesting that conception in space might form part of space tourism. What an amazing thing to be able to say, well, I was conceived in space. How about that? There are a number of proposals for space stations at the moment. Axiom has actually started building theirs, so looks as if it's definitely going to happen. It also looks as if Blue Origin's orbital reef will definitely happen. Over the past couple of years, there have been a few proposals for space hotels. The fact that some of them haven't really advanced makes me a bit skeptical about whether they are actually going to happen, but nonetheless, they're still a cool idea. This one is my favourite. It's a bit like the rotating space station in 2001, A Space Odyssey. However, this was only Mark 1 of the proposal, and it looks as if it's been recycled into the Voyager concept. Poor old Dr. von Braun has been dropped, but the same concept of a rotating wheel providing some form of artificial gravity. So I think I've probably raised more questions than I've answered, but I hope you've enjoyed this little tour through some of the issues which exist or might exist when it comes to human reproduction in space. And I think the take-home message is there's still a lot we need to know before we start experimenting with humans, and we also need to stop treating the issue as the elephant in the room and actually bring it out into the open. So finally, just to answer your questions while we're having a look at some potential bases on the Moon and Mars. The nationality of a baby born in space will be the nationality of the spacecraft or habitation that it's living in. Is a normal pregnancy feasible in space? I don't think so, unless artificial gravity is available. Will we be able to have children on Mars? The answer is probably, but at the moment the question is, should we? Because we just don't know the implications for child growth and development. What will hypergravity do to a child's musculoskeletal development? I think especially if it's microgravity, it won't do it any good at all, and potentially the child would just not develop normal bones and muscles if there were insufficient countermeasures available. And how can we ensure healthy bone formation in children in space? I guess the only things that we can do is what we do for adult astronauts. We give them drugs, we get them to exercise 2 hours a day, but those sort of modalities are probably neither practical nor sensible with really young children. So artificial gravity really is going to be the only answer when it comes to that. Thank you very much for your attention today. If you have any further questions, feel free to contact me, and I'd also like to recommend the Ad Astra Vita Project website for you as a resources portal for space health and medicine in extreme environments. Thank you.